Well, good afternoon, everybody. Good afternoon, everybody. Welcome to SVS401, migrating microservices to mainframes. Oh, no, different talk. You are in the right place. You are in the right place. Best practices for advanced serverless developers. Welcome, everybody, here in the room as well. There's actually an overflow room somewhere in the greater Las Vegas area, so hello to you if you're there as well. And also, if you're watching this in the future on the recording, hello to you as well. My name's Julian Wood. I've got slightly longer hair after lockdown. But yeah, I work as a part of a super cool team within the serverless product org at AWS. And I love helping developers and builders understand how best to build serverless applications and run them, and also be your voices internally to make sure we're doing the right thing and building the best serverless products and features. Now, first of all, don't get intimidated. This is not a story about for only advanced serverless developers. There are best practices here for everybody, even for people who are dipping their toes into the water and wanting to understand serverless. So there's plenty to talk about today, which I hope is relevant. Now, this talking about best practices for serverless is an extremely broad topic, which I'm going to cover in 6 sort of broad areas. And this is a 400-level talk, but each area of these could be 400-level on itself. So I've decided to err on the side of sharing more content and more information rather than less. Now, if you were here last year, I did a similar talk, but I've actually gone broader in some areas and deeper in other areas. So some best practices have had to sit on the bench for this year, but so if anything is missing from last year, please don't think that they're not best practices. They're all still worth considering. They're all still applicable, just we're going to add some more today. So I am planning on covering a lot today, and I'm going to give you some jumping off points to be some more content and information to dive deeper. The slides and the talk are going to be posted later, and this handy reference page is there for you as well, and I will share it again at the end, so don't worry, with all the best practices you need to best fit your serverless applications. Now, on Friday, I fractured my jaw, so if I do a mumble a bit or whatever, we'll just have to keep going. Let's see how we do it. So, ready? I need a deep breath. Are you ready? Let's start. So it may sound odd, but it's worth asking, actually, a fundamental question at the beginning: what actually is serverless? We commonly think of the start of serverless when Lambda was announced at reInvent 8 years ago today. Imagine that. But it's interesting to note that there wasn't actually any mention of serverless during the announcement. And actually, AWS was founded on serverless because we wanted better, scalable ways to build applications. So services like S3 and SQS, the first sort of 2 services that AWS even released, are very common serverless services. And these came out even before EC2 and certainly way before Lambda. We always had the idea to make consuming the cloud simpler, and a serverless approach has always been the best way. Now, we can turn ourselves sort of into pretzels to try and define what is and what isn't truly serverless. When it seems like sometimes everything could be a little bit serverless, but it's not actually about the servers or the lack of them, and it's just like Wi-Fi, or as we call it, wireless. You use Wi-Fi without thinking of the wires, but there are a heck of a lot of wires in wireless. They're just behind the scenes, and you don't have to think about them. So I'd like you to rather consider serverless as a mindset, maybe, an approach to building applications that focuses on the business value rather than the servers underneath them or the enabling technology. And the benefits are clear: faster getting apps from prototype to production with fast feedback cycles, which lets you quickly iterate on your business. And really, we all think, and I hope you think, it's the best way to build and run modern applications with the lowest cost of ownership. But a mindset isn't something that you can build apps with. So in a more practical term, how about thinking of serverless as an operational model, explicitly avoiding taking on operational tasks and trying to outsource as much sysadmin tasks as possible. And think of every non-serverless component as something you need to do, and try and sort of avoid that. Additional responsibility that you rather make a choice now to be able to optimize your future maintenance. And please also don't think of serverless as no-ops. There's certainly lots of operations that's going to happen, but it is a bit different. And the idea is that you offload some of your operations to a provider so you can focus on your business operations more. And also, why not let AWS be your platform to be able to augment your developers, your operations, and your platform's teams? And this allows you a concept of also enabling you to build within the cloud, so you can take advantage of all the security, agility, and scale, and not just building on top of the cloud with having to use abstractions that make you do more. You can concentrate on the flow of data and events. And with this approach, you find you land up building event-driven applications where you focus on producing, consuming, and reacting to a stream of events. And services being loosely coupled, distributed, and super flexible at any scale. But let's not kid ourselves that there aren't any trade-offs. Good architects always do need to be thinking about trade-offs. It is a different way of building with more moving things. You need to understand how data moves and persists with different development and operational practices, and embracing the cloud maybe a little bit more than you've done before. And companies who are doing this, like Liberty Mutual, who, like many others, see the serverless mindset as the whole benefit of serverless, improving agility and reducing costs by having a strategic and pragmatic serverless-first strategy. Note that it isn't serverless only, but they consider a serverless approach the default starting point as their architecture or service of choice. If another non-serverless option will result in a better product, well, then they go for that, but with a good reason. And I promise I'm not only mentioning Liberty Mutual because heroes like Matt Coulter and Kirsty Perot, among others at Liberty, who are awesome gurus, and you should really follow what they have to say. Now, companies succeeding with serverless think cleverly about their entire IT organization. They work hard to build a curated experience for developers and builders, which they see as their platform with what's called enabling constraints. Can you give teams a fast feedback loop to give them confidence that they're doing the right thing? And when they stray, here's some feedback to remedy early, which is a super useful gift. Now, serverless has made it much easier for builders to own deployments and infrastructure as code tools, infrastructure as code more. And it's often about building that paved path. Here are some commodity good practices that maybe hopefully have been codified to guide you on the journey to a good serverless solution. So serverless first and enabling constraints speed up the decision-making process and allow for rapid development. And many times companies try this with a sort of top-down approach, well-meaning, overarching central platform or security teams blocking things really late in the development lifecycle, which, that can be frustrating. And dev teams feel like it's putting the no in innovation. To be more successful using a serverless approach requires us maybe to turn things around our head and view things like security and have a development teams being enabled by security rather than what sometimes feels like being held hostage from deploying or innovating. And so having a platform team, security team, or a larger cloud center of excellence be a bottom-up enabling function with appropriate top-down strategy and controls to find issues and mistakes and course correct quickly. And platform as a product is a good way to think about it to improve developer experience and deliver better business outcomes. And so what does this mean? Well, this means getting your enabling platform teams, or those CCOEs, to focus on accelerating agility. That's the key term. Smooth those CI/CD pipelines, automate the account vending process. Maybe they can manage the connections to third-party systems. They can create robust guardrails, which can be processes, preferably automated, to reduce the blast radius of any bad app behavior. And they can use other services like Control Tower, define SCPs and permissions boundaries, and get great at things like CFN lint or CFN nag, and use other governance tools as safeguards to ensure your builders are doing the right thing. And maybe a team can look after central network connectivity and VPCs, for example. That's something they can do. And then the cool idea is that this should all be shareable and scalable, helping other teams make the agility leap. So they can be collaborative by using things like CDK constructs or blessed serverless patterns as building blocks to give your builders the runway so they can go faster, safer. And then always think about how you can help and support without creating a bottleneck. And one approach worth looking at codifying is the recently updated serverless lens of the well-architected framework. And this is packed with best practices. And I've actually done a whole blog post series delving into all the questions of the well-architected framework and how they apply when you're building and running serverless applications. If a lot of serverless sounds like it could be lock-in, well, how do we think about that? My great colleague, Gregor Hoppe, says, when considering lock-in, it may be worth changing your mind up a little bit and beware of what he calls mental lock-in. In his recent post, he eloquently says you can reduce lock-in in two ways: reducing how much it costs to change and reducing the likelihood of having to change. Now, if you're building well-architected serverless applications with defined patterns and good automation, you can increase the speed in which you can make changes. And if you increase the speed of delivery, which is your velocity, you can change decisions quickly. And this really helps actually to mitigate some lock-in. Certainly something worth thinking about, and please make sure to watch Gregor's talk where he's going to go into more detail. And some more superb Liberty IT alums, including Dave Anderson, who created that serverless first mindset at Liberty IT, have written this great book, and it's actually, I think, out tomorrow. So please have a look. And it's called The Value Flywheel Effect: Power the Future and Accelerate Your Organization to the Modern Cloud. And I really suggest reading this to understand how you can create an adaptive organization to do serverless first at scale. And this is, of course, available at all good Amazon bookstores. So to think serverless as a mindset and focusing on business value rather than what the servers are doing or what they're not doing. Optimize for long-term operations and building within the cloud, not just on top of it. So you can concentrate on the flow of data to build event-driven applications. And also empower your platform teams to enable the rest of your business with well-architected goodness. And try thinking of serverless first. So as builders building event-driven applications, which means events, it's worth talking a little about state. With only relying on synchronous workflows to connect different parts of your application, you can get into quite a bit of trouble with sort of additional latency and some failure modes which complicate recovery. So we really want to be looking at asynchronous patterns to reduce latency and add more resiliency with loosely coupled systems. And async doesn't have to mean just behind an API. We've got a number of very powerful serverless messaging services that your application components can use to handle asynchronous communication. You know, SQS for queues, SNS for topics, EventBridge is a event bus for routing, and Kinesis for streaming. And there are some others as well. But to drill into one of them, we have a specific service for event routing called EventBridge. And this allows you to receive events from a number of sources, and these can be AWS sources, they can be your own applications, or custom applications, or your own SaaS applications from providers like MongoDB and Datadog and Okta and Salesforce. And it makes it really easy that these events can then flow into different event buses within EventBridge, and then you can write very clever and sophisticated rules to route the events to any number of targets. These can be other AWS services, other buses, or in fact, any API on the internet. And this allows you to create a really wide variety of integration patterns. And at the heart of it, it's really important to think of events as, which my clever colleague Dave Boyne says, are the language of serverless applications. And these flow through an event-driven architecture which allow us to create distributed systems, keeping components decoupled using a messaging service in between. And consumers can come and go over time, and we can add to them easily with the events that we create, creating a flexible, evolutionary architecture. But everyone's always wondering, well, what information should we actually put into our events? And so here are some ideas for enriching events to add useful and helpful information without having too much information. So with an EventBridge event, you have the event envelope and the detail field, where you can put your event content. And if you control the producer like a Lambda function, a really good idea is to add a resources field to the envelope so downstream resources know where the event came from. And this can help with operations and observability. Now, looking a bit more detail into the structures of the details field, it can be useful to add some event metadata about what service, environment, or domain the event is part of. And as you decouple across boundaries, this can help piecing the flow of events together. And maybe you can think of adding a correlation ID, which can be helpful for tracing, or also used as an idempotency token. Then within the detailed data itself, this is where you place the event information itself. And here I've added an order ID and a user ID, for example, in the data field. And then the downstream consuming service can use this in further processing. All good. However, we're actually now creating some coupling. Ideally, we'd want to have perfectly decoupled systems when producers don't need to consider the subscriber. But in this example, the downstream services now need to call back to the order service to retrieve details about the order or user to act on that event. And now we're back to more tightly coupled architectures. And so in reality, we do need to think about what event content we want to send, depending on what data is needed elsewhere. And maybe what services are going to act on that event and how we're then going to define our bounded contexts. Now, a way to avoid the coupling is to perhaps add more information into the data field with what you think downstream sources will need, what the consumers will need. And you may need a version schema to do this, to keep track of things. And so here, adding the order and user detail to the event. And this is a useful pattern called event carried state transfer, where event state flows through your services and a downstream service can build up its own local cache view of what data it needs, which it can augment, enrich, and send on. And it may only need to hold onto a temporary. And so using event-carried state transfer can be very powerful to give you decoupling you need with enough temporary local data to act on something without getting into distributed state issues. Then consumers come and go over time, and we can add to them easily with the events that we create. So you also unintentionally don't want to expose any implementation details. The order details, for example, may not contain enough information, or maybe doesn't have enough context. What actually is the amount, and does the address have enough information to send something for the downstream service to act on? And are you leaking any PII information which you may not want downstream services to even see? So this is certainly worth considering as you move events around your applications. So when thinking about state with events, think of your events as the language of serverless applications when using asynchronous calls with one or many messaging services. Enrich events with content and metadata to make them more useful to other services. And consider event-carried state transfer to decouple usefully while always considering the trade-offs. Now, the next topic to cover is serviceful serverless, using configuration rather as code and using managed services and features where possible. When we often think about a serverless application, one with Lambda, which we know can be written in a number of languages, you can even bring your own, we have an event source which triggers the Lambda function based on a change or request, and then performs some action on the event and sends it to another service. And this is a very common Lambda-based serverless application. But what if you could actually remove the Lambda function and have an event source or something else talk directly to a destination service, not having to maintain your own code? And this is a direct service integration. This is called being serviceful. And you want to be using Lambda when you need it, certainly to transform data and not transport it. This is a great quote from one of the fathers of Lambda, who's now the GM at Nair. If you're just copying data around, there are certainly other ways. Another thing to think about is how much logic are you actually squeezing into your code? Are you adding more and more functionality to a Lambda function, doing everything in code, if-thens and decisions and all that kind of thing, that becomes what we call a Lambda lift, getting rather large and unwieldy? Or another way, how little logic are you actually invoking in a Lambda function? Do you have a whole lot of code in your Lambda function that isn't doing much? It's adding complexity, it's more stuff to test and secure that you're not in the end using. And this often starts with good intentions. You're moving to the cloud, you have an app that sits on-prem, in a VM, in a container, and it has a whole lot of the components and functions of the app in a single place. And so you move it to the cloud and wisely choose Lambda for your compute, maybe sticking an API in front of it and using some sort of storage, but all those components and complexity just move to your Lambda function. So when you ultimately really should be migrating those components into separate discrete services, using the best service for the job. Move your front into S3, get API gateway to handle your auth, caching, routing, and throttling, for example, and then using the messaging services I spoke about asynchronously, offload transactions to a workflow as well, and use the native service error handling and retries. And also split your Lambda functions up into discrete components, each with a single purpose. This all helps you to scale your application, provide higher resilience, improved security, and lower costs. Another aspect to think about is how you can effectively use orchestration and choreography as communications model for your serverless apps. And rather than writing your own code, manage this as configuration. In orchestration, communication is more tightly controlled, using a central service to coordinate the interaction and order in which services are used. Choreography communicates without that tight control. Events flow between services without any centralized coordination. And many applications use both choreography and orchestration for different use cases. Step functions is an excellent example of an orchestrator as a workflow service for transactions to coordinate the components of a distributed application using visual workflows. It has branching, it has error handling, and a lot of built-in other kind of things. And then Event Bridge is great for choreographing different parts of your application by producing and consuming events which flow through and between your more distributed applications. And even within these services, there are ways to reduce code and even be more efficient. Step Functions now has the awesome SDK integrations. This means you can call any AWS SDK action. That's like over 9,000 of them directly from Step Functions without even having to use a Lambda function. EventBridge also has got API destinations, which allows you to call any API on the internet directly from EventBridge with security, retries, and throttling just built into the service. Two great ways to use direct service integrations and reduce your custom Lambda code. Even within step functions, there's more. They came out recently with intrinsic functions. And you know those tiny little Lambda functions you maybe had to do some JSON manipulation, math or string operations? Well, now you can do that directly with step functions. Allows you to reduce code and maintenance using out-of-the-box functionality when building your workflows. Now, when building with step functions, you don't have to start from scratch. Our team has put together the awesome Serverless Workflows collection, pre-built, open source step functions workflows on serverlessland.com for a whole bunch of patterns that you can add to your apps and modify as you need to. So with all this serviceful stuff, remember, the best performing and cheapest Lambda function is the one you remove and replace with a built-in integration. So serviceful serverless, that's all about using native service integrations, avoid coding when you don't have to, using Lambda to transform, not transport, and use the various messaging services to communicate between services. Smaller, nimbler, more secure, single-purpose Lambda functions, using more services as you need to. Go on, it's not that hard. Just add another queue or another EventBridge rule. Use step functions for your workflow orchestrations needs, using as many features, and let EventBridge handle your event routing. So I am suggesting not using Lambda where you can, but Lambda is still an important part of many serverless applications to run your business logic and has some amazing capabilities as a service which are worth understanding and exploring. Lambda has two types of invocation models, synchronous. On the left, the caller calls Lambda. This is either directly via the CLI or the SDK, or the newish function URLs, or through a service like API Gateway, which is then mapped to a Lambda function. And this sends the request event to the Lambda function, which does its processing, waits for a response before returning it back to the client. When you invoke a function asynchronously, either via a client call or an S3 change notification, or a service like EventBridge sending an event when a rule is matched, you don't actually wait for the response from the function code. You hand off the event to Lambda, and Lambda handles the rest. It places the event technically in an internal queue, and then returns a success response to the caller saying, yep, I got your event. A separate process then reads the events from the internal queue and sends them to your function. There's no actual direct return path to the calling service. Lambda also has some great polling capabilities for a number of service integrations. An event source mapping is a Lambda polar resource that reads items from Kinesis or DynamoDB, your own SQS queues or Kafka sources, including self-hosted Kafka. Yeah, that's not even an AWS service, as well as Amazon MQ for Rabbit and ActiveMQ. And then the pollers pull messages from these sources, and you can optionally filter them. And this is super useful functionality built just right into the system. It helps reduce traffic to your functions, simplifies code, and reduces cost. Then what it does, the pollers batch records up into a single payload and send it to your Lambda function for processing. And then we actually manage these pollers for you. It's part of the Lambda service, which is a huge benefit. You don't have to pay to run and scale your own consumer EC2 instances or containers to pull for messages, and it's actually free. You don't even pay above your function invokes for the service. Just more of what Lambda can do for you. So now switching to the Lambda execution lifecycle and what it looks like. There are actually three phases: an init phase, an invoke phase, an additional shutdown phase I'm not showing here. When a request comes in for your first invoke of a function, Lambda runs the first part of the init process, which first creates a new execution environment based on your function configuration. And just the timeline goes from left to right. And the secure execution environment is a secure, isolated runtime that sits within a micro VM to run your code. And it's not shared between any other Lambda function, let alone any other customer or account. Lambda then downloads the code, downloads all your Lambda layers or your container image. It then initializes the language runtime, so this is Node and Java and Python, for example, and then runs your function initialization code. And this is the code outside the handler. And this sort of completes what's called the cold phase in its stage. And then the invoke starts. And this takes the event, runs your handler code, receives the payload and the business logic. And then once the invoke is complete, the execution environment actually stays available to run your handler again without having to run the cold start, and so this is called a warm start. And there's actually a separation of duties, which is important for optimization, the part that AWS controls and your code, which you control. And in a standard function configuration, it's at the line just before the pre-handler code runs. However, you can also use cool new features like Lambda extensions or runtime modifications to control part of how Lambda works. So your optimization shifts a little bit less left in the timeline, where you control the extensions code and how the runtime starts up. So as we know, cold starts happen when Lambda is scaling to process new events, or you configure provision concurrency. Also, cold starts always happen when you update the function code or configuration, as this is seen as a new deploy, and the function lifecycle starts again. And these are actions that you choose to do. Now, cold starts can also happen as part of Lambda managing the service for you. We periodically, but it's not very often, but we do need to refresh execution environments to keep them fresh. If we need to replace any failed resources, or when we need to rebalance requests across AZs, as Lambda is by default a multi-AZ service, and we want to manage high availability as best we can. And so these cold starts you can't control. They're a part of Lambda managing the service, but it's worth knowing about. So cold starts in terms of timing, they vary from literally under 100 milliseconds to a few seconds, depending on what's actually what they are doing. And it's actually, cold starts is a very small percentage of cold starts. When developers are building and testing their functions, they are building on every single deploy. And every single deploy is going to be a cold start because it's a new function. And so developers are like, oh, panic, panic, this is what production's going to look like. But actually, at scale, this doesn't happen. The more requests you have, the smaller the percentage of cold starts, because you have more execution environments, more warm starts, and so those cold starts are reduced. And so another thing as well is cold starts when connecting to a VPC. Used to take a lot bit longer. That is all solved. This was reduced in 2019 with a networking change, and so cold starts and a VPC is no longer an issue. But a major portion of cold starts is actually what's handling in the pre-handler init code. This is your code where you're going to be importing SDKs, you're going to be importing software libraries, you're going to be gathering secrets and establishing some database connections. And typically, it's good to do this in advance of invokes, because then you can use these libraries and connections for subsequent warm invokes. But what can you do, and what best practices can you think of to help out here? Well, first of all, don't load it if you don't need it. Really optimize loading any dependencies to load only the modules to reduce the amount of code you run, the deployment package size, which speeds up cold starts. So rather have small purpose-built Lambda functions, as I previously mentioned, so you're not loading a bunch of stuff the invoke doesn't need. What you can also do is lazily initialize shared libraries, I'll show you shortly, if you do have multiple functions per file. And then the pre-handler code, as I said, is great for establishing connections, but also be prepared to then handle reconnections for the further warm invokes. Then for HTTP connections, you would really want to be setting keep alives in the SDKs. And then think of execution environment reuse. Super useful to be able to store data for a subsequent invoke, can be useful, but also be careful what you're going to carry. You know, if you have secrets for subsequent invokes that you don't want to carry on, be careful that you're clearing them out before the next invoke. If you don't like cold starts at all, you can manage provision concurrency on your functions with no additional code changes. So some more on optimizing dependencies, only using what you need, and running some example tests, which we did. If you need to use the DynamoDB SDK, including that specific package instead of the whole SDK, can be up to 125 milliseconds faster. Also, similarly for X-ray, adding -core to the package name parameter in required took off 5 milliseconds. And in a test with X-ray, switching the methods and providing the document DB client reference was 140 milliseconds faster. So being more specific means the code references a smaller package, and it's faster to initialize during the cold start. It's also worth thinking about using the Node version 3 SDK, which is 3 meg in size rather than 8 meg in size for version 2. And actually, this is now the default for the recently released Node 18 Lambda managed runtime. And with the version 3, you only need to import the packages you actually need instead of the whole one. So these are now in different modules. Also, it's cool, TCP connection reuse is now on by default, which is going to help speeding up connections. And there's a whole bunch of additional helpful functionality worth looking at. But remember, it's not actually a straight switchover. You do need to do some code work to take advantage of it. So think of this especially when moving to Node 18. So looking further at the lazy initialization, which is having multiple handlers in a single function. And here's a Python example. First, we import the botter3 module, and then set 2 global variables for the S3 and DynamoDB clients. Then what we do is in get objects, we check if the S3 has been initialized. If not, we initialize it. Same thing for get items in Dynamo, and this means that instead of doing both in the initialization phase, you can make individual calls more responsive when sharing global objects across multiple functions. It's one way of doing things. However, if you're using provision concurrency, this isn't going to help you at all. Now, another optimization to look at is running your functions on ARM-based AWS-built Graviton2 processors. And you can get up to 34% better price and performance compared to x86. How about that? And in many cases, it's just a simple architecture change, sort of like flipping a switch. And interpreted and bytecode languages like Node and Python and some Java can run without any changes. You just change the architecture. But compiled languages do need to be recompiled for ARM64, and if you're using container images, you do need to build these specifically for ARM. And most AWS tools and SDKs do support Graviton2 transparently, so I really suggest trying it out, and extra saving you money, which is always a good thing. Another thing to understand with Lambda is how memory is the power lever of the function. This is actually the only performance configuration you can control. And you can allocate from 128 meg all the way up to 10 gig in 1 meg increments for your functions. When you do increase the memory, AWS proportionally increases the number of virtual CPUs and the network bandwidth allocated to the function. So if you do have code that's constrained by memory, CPU, or network, adding more memory can improve performance and reduce cost. Now, with all of the larger function memory size, this proportionally translates to up to 6 virtual CPUs, depending on how much memory you configure. And this means you can use Lambda to run some pretty huge and important memory and CPU-intensive workloads. And any Lambda functions with memory allocated that also gives you more than one CPU core, then CPU-bound workloads will see gains, but of course they do need to be multi-threaded. And something to consider is matching the memory allocation to your business logic, having smart memory allocation, for want of a term. And here I've got some results from a function that calculates all prime numbers under a million 1,000 times. I tried some memory configurations between 128 meg to 1 gig. And I can see the best and worst performing configurations in terms of time in seconds and in terms of cost. Yet the difference in time between the best and worst performing functions is more than 10 seconds. Yet the additional cost to run the faster function is only a fraction of a cent because there's more memory. So you can get dramatically faster invoke time for very little additional cost, which may be super useful to your workload. Now, working out the optimal memory configuration can be a bit of a super manual process if you try all the possible memory configurations and do it all yourself. So Lambda Power Tuner is an open source tool that gives you a data-driven approach to help you visualize and fine-tune the memory power configuration to optimize your Lambda functions. Actually, behind the scenes, it uses a step function state machine to run multiple concurrent versions of your function at different memory configurations and measure how they perform. And this isn't a theoretical thing. It runs in your account using your real function calls, showing the real cost and speed to find the right balance of memory in an automated way, and can even be plugged into your CI/CD process to analyze your functions. And you can also now compare the values of 2 different functions graphically, which is super useful to compare different functions before and after when you make a change. And also, you can even compare when looking at migrating to Graviton2, as it's able to compute costs separately for both architecture. This example function here is the ARM one is 27% faster and 41% cheaper than the x86 version. So you've tested this out. This function would be a great choice to move over to Graviton2. And Power Tuner is a super helpful tool to give you the right memory configuration for your real-life workloads. And a common question we get often is about connecting your functions to a VPC and whether you actually need to. If you do have resources in a VPC that your functions need access to, Lambda can easily connect to them. Lambda functions continue to run in the Lambda service VPC and attach via an ENI to your own VPC to then connect to VPC resources. And this setup is actually done on the function creation, so it doesn't have any impact at all on cold start times. However, you don't actually have to connect your functions to a VPC to make it necessarily more secure, because all internal AWS traffic uses the global backbone and is encrypted, so it's not just open onto the internet. However, if you do want additional network routing control or egress access control or more visibility with VPC flow logs, then it's really great you can use VPC features for this. And yeah, if you want to use a VPC, Lambda works great. But since we're looking at the Lambda lifecycle earlier, it's worth also switching to talk about concurrency. Concurrency is the number of requests that your function is serving at any given time. Think of it as simultaneous processing. When your function invokes, Lambda processes an instance of it as that execution environment to process the event, and only processes a single event at a time, regardless of how it was invoked. Batches pulled off a service may have multiple items in the batch, but it's still considered a single event and invocation. So following the timeline, a single request comes in, Lambda runs the cold start, and then invokes the function. And as the function can only handle one request at a time, the execution environment is blocked for this time. If the function is invoked again while a request is still processed, another execution environment, another instance is provisioned, increasing the function's concurrency. When the function code finishes running, it is able to handle another request. And here you can see request 1 has completed. It is now warm and free, as we saw earlier. And this process continues as subsequent requests come in, reusing execution environments when they're available, and creating new execution environments when we need more, increasing concurrency. And you can count concurrency as the number of simultaneous or parallel requests and invokes happen for a single execution environment. The number of concurrent requests is always 1. And here you can see how it fluctuates as cold and warm starts happen, with the concurrency always equal to the running number of execution environments. And you can view concurrency using the CloudWatch concurrent executions metrics for all or individual functions. So how does concurrency then relate to transactions per second? The number of transactions Lambda can process per second is the sum of all invokes for that period of time. If a function takes 1 second to run and 10 invokes happen concurrently, Lambda creates 10 execution environments, and in this case, Lambda processes 10 requests per second. If the function duration is halved to 500 milliseconds, the Lambda concurrency remains 10. There's still 10 execution environments processing requests. However, they are reused within the second, and transactions per second are now 20. Also, you can use reserve concurrency to allocate a maximum concurrency for a given function, a maximum number of requests a function can run in parallel. And this reserves that concurrency for a particular function from the account's quota. I'm going to cover that shortly. But this, in effect, protects and ensures that a function is always able to scale up to the reserved concurrency value. And there are 2 additional use cases for this. You can set or limit a maximum function concurrency to protect downstream resources. If a database or an external API can only handle 50 concurrent connections, well, you can ensure Lambda can't scale beyond 50 concurrent invokes and overwhelm the downstream service. And you can also set your function concurrency to 0. And this basically stops invokes. And you can use this to stop Lambda processing if you have an issue with a downstream service. And it can actually give you some time to fix whatever the issue is before dialing Lambda up again. The other control is provision concurrency, which allows you to set a minimum number of available execution environments for a published function published version. And this, in effect, is running the cold start process in advance by sort of pre-warming your functions. And this is useful for many synchronous requests when you want to ensure that you have enough Lambda environments ready to go for an anticipated traffic spike. Maybe you've got a big sale at 8 a.m. or you're streaming a TV show at 9 p.m. You can to be able to handle the load. And you can still burst using standard concurrency afterwards, and provision concurrency can actually even save you costs in certain situations. But there are also some concurrency quotas to bear in mind. The burst concurrency quota gives you an initial burst of traffic for each function. And this is between 500 and 1,000 per minute, depending on the region. And after this initial burst, functions can then scale by another 500 instances per minute. There's also an account concurrency quota, which is the maximum concurrency for a particular region. And this is shared between all functions in an account in that region. And this defaults to 1,000, but it can be easily raised to sort of quite ridiculous amounts, to be fair. Now, remember the reserved concurrency I spoke about earlier? Well, this is the pool from which that reserved concurrency is taken from. So let's see how account and burst concurrency play out visually for an example application. Anticipating handler additioning load, we've got some good application builders who've already raised the account concurrency limit to 7,000. There are no other functions in this account, so it can use all available account concurrency. Just before 9 a.m., the application is ticking along already as a steady stream of requests using 1,000 concurrent execution environments. Each Lambda invoke takes 250 milliseconds, so transactions per second would be 4,000. At 9 a.m., there's a large spike in traffic, 5,000 sustained requests. 1,000 requests then use the existing execution environments. Lambda uses the 3,000 available burst concurrency to create new execution environments to handle the additional load. Now, at this stage, 1,000 requests are throttled, as there's not enough burst concurrency to handle all 5,000 requests. Transactions per second are 16,000. And the blue line with the white dots is looking at the burst quota available if you're going to be following. And now in the next minute, Lambda scales by another 500 concurrent invokes. 500 requests are still going to be throttled. Next minute, Lambda scales by another 500 requests per minute. Now no requests are being throttled. The application can now handle all 5,000 requests. And the app would continue to handle the sustained 5,000 requests, and the burst capacity quota over a minute is then going to raise to 1,000. And then, oh dear, 4 minutes pass, the app sees another huge spike in traffic, but this time it's unexpected. 3,000 new sustained requests arrive for a total of 8,000. So 5,000 requests are going to use the existing execution environments. Lambda uses the now available burst of 1,000 to create new environments to handle that load, but 1,000 requests are going to be throttled as there's not enough burst concurrency, and then another 1,000 requests are throttled as the account concurrency quota, the sort of ceiling, has been reached. Another minute, Lambda scales by another 500 concurrent requests. Burst concurrency throttles 500. Account concurrency is still going to throttle another 1,000. Lambda scales by another 500 current requests. 1,000 requests still throttled by the account concurrency. And this is then going to carry on. As the app continues to handle the sustained 5,000 requests, but 1,000 requests are always still going to be throttled by the account concurrency quota, which of course you can then raise again and sort that out. So in 7 minutes, the function is scaled from 4,000 to 28,000 transactions per second. So it's really worth you taking the time to understand the different invoke modes and how Lambda lifecycle works to make use of execution environment reuse with warm starts. I've given you some helpful tips on optimizing those cold starts when you do get them, and how to save money and get more performance by running your functions on Graviton 2. Using memory as the power lever for your function, which adds more CPU and network, and I covered how you can measure different memory allocations for optimization, whether you need to connect your functions to a VPC, and diving super deep into how concurrency and quotas work so you can scale Lambda exactly when you need to. So next up, I'd like to talk about configuration as code. This is all about using infrastructure as code to give you awesome superpowers when developing and deploying your serverless applications. Infrastructure as code is all about being able to define your application resources and setting up your infrastructure using a configuration file, in effect, treating configuration files as software code. And this allows you to track it in a Git repo. You can do things like version control, do pull requests, reviews, you name it, just like you can do with software code. It also allows you to then automate the provisioning process, which gives you robust, repeatable deployments, getting rid of configuration drift, and allows you to deploy the app to multiple environments and accounts, which can help in a number of ways. Now, for serverless, there are a number of specific infrastructure as code tools to define your cloud resources. From AWS, we've got the Serverless Application Model, or SAM, an open source framework, and there's also Cloud Development Kit, or CDK, again open source to define cloud resources using familiar programming languages. And both expand the syntax and generate CloudFormation under the hood. And there are also a number of great third-party tools which you can use. And you really want to be using a framework to build your serverless applications and get into the habit of starting with a framework rather than building stuff in the console. So let's have a look at SAM with a lovely squirrel mascot. SAM comes in two parts, a transform component on the left, which generates CloudFormation based on your config files, and a CLI on the right, which provides a whole bunch of tooling to help you with local and cloud development, debugging, packaging, deployment, and more. For example, just 20 lines of code can generate a bunch of resources which are linked together. This SAM template generates an API gateway endpoint connected to a Lambda function which reads from a DynamoDB table with an associated IAM role. Now, it's cool that SAM can generate all these resources, but we also want to make sure that we bake in security best practices into anything we do. And of course, it's the easy option to give star permissions to actions and resources to get things working. But obviously, this is a really bad practice and something you should avoid at all costs. Now, after the fact, you can validate the policies using IAM Access Analyzer. It's got 100 policy checks with security warnings for overly permissive policies. But SAM has some handy and easy to use built-in IAM policy templates to scope the permissions of your Lambda functions while you're creating them. So in the previous template, I showed that the Lambda function talks to Dynamo, but only needs read access. So instead of having to type up and manually craft a whole IAM policy, I can simply add DynamoDB read policy, referencing the table in the template, and SAM creates the necessary scope down IAM role and policy. There are more than 75 available policies covering a huge amount of services that your Lambda function may need to interact with. So SAM policy templates makes it much easier to use the right least privileged permissions to make your applications more secure. But SAM has also come out recently with SAM connectors. These are a CloudFormation resource to connect your resources together. You simply add the source and the destination and whether you want read and write permissions, and SAM just figures it all out. And this is especially useful for connecting non-Lambda resources together, so you don't have to remember on which side of the connection you need to do the permissioning, which I know can get a little bit complicated. But some other SAM useful tips. Don't hard code your names. Get SAM to do your naming, which makes it much easier to reuse. And also don't forget SAM delete, which can delete all your resources directly from the command line. SAM also has branched out from CloudFormation as well with a preview for local testing using HashiCorp Terraform. I mean, we have many customers who love and use Terraform, so this is the first step on hopefully a long journey to make SAM and Terraform work better together. There's also the great and new complete SAM workshop, which takes you through a lot of the serverless development lifecycle and how SAM can help. And if you're building applications using a framework, as you should, you don't actually have to start from scratch. The Serverless Patterns Collection is a great resource on serverlessland.com. It's now got more than 400 sample SAM, CDK, and Terraform code patterns across many languages and services for your service integrations. So using things like API Gateway and Lambda, there's a pattern for that. Throw in AppSync and Cognito and Kinesis, EventBridge, you name it. There may be an existing pattern already, which you can copy and paste and use your own. Or submit your own. It's all open source, and you can help out your fellow serverless builders. So when thinking about life-changing configuration as code, use a framework. This gives you a number of superpowers, being able to programmatically create infrastructure and store its template in a repo and make it reusable. Sure, you use better security using policy templates and SAM connectors, and to get started with the Serverless Patterns Collection. So configuration as code steps definitely into the next section, which is talking about the software development lifecycle, getting code from your laptop out into the world. A traditional developer workflow is often done on your local machine. Developers use the following workflow before committing code, and it's you to write code, save code, run code, and check the results. And this is called the inner loop, and it helps you get fast feedback while building your applications. Now, to do this, many developers think they need to be able to run their entire app locally to have a fast inner loop cycle. However, when you're building cloud and serverless applications, sure, you've got a lot of code that you're developing, but there's also a lot of interaction with other services, sending events and messages or connecting to other APIs, or talking to databases. And then how are you going to test all of this? But actually, what's more important to devs than testing quickly is actually testing quickly, not just testing locally. Now, it can be tempting to try and emulate all of these other services on your local laptop so you can test quickly, but this is hard. You, first of all, may not have mocks or emulators for all the services that you'll use, and emulators will never really support the latest and greatest features. You'll end up often spending more time managing your emulators than managing your code, so try and avoid this if you can. However, to be fair, emulators for functional web apps are really worth looking at. Something like Architect, if you're using that, it's going to be certainly useful. So locally, you can use sparingly some mock frameworks for complex logic, and you should definitely mock your event payload so you can provide input to your business logic and test your functions locally. And so you really want the best of both worlds. You want to be able to do local, and you want to be able to do cloud. So you want to iterate locally on your business logic and run your code in an actual cloud environment as soon as possible. And this allows you to test Lambda or API Gateway really quickly locally and then communicate with actual services in the cloud, which is where they're going to run anyway. You also want to be then running your integration tests in the cloud, which makes it much more accurate as you're not trying to fudge things like security just to get your tests to work. Now, previously, it's always sounded like a good idea, but it wasn't really easy to do. So the SAM team, again, has come out with SAM Accelerate to fix just this. So while you're developing, you can iterate against the cloud with the speed of local development. 3 main components. SAM Build builds only the parts of your code that have changed. SAM Sync then initially syncs your template to the cloud. You can then iterate locally, unit test your function locally, test your APIs locally, but the rest of your infrastructure is already deployed in the cloud. When you then make changes, SAM watches your local template file, your template and your file code, and then only needs to rebuild and sync what has changed, making it much faster. When you save your code in the background, it quickly syncs your code changes to the cloud. And this is really fast. It actually uses the service's native APIs rather than waiting for a whole CloudFormation redeploy. SAM Logs also gives you aggregated feedback from multiple log streams and traces directly in your terminal. And so this amplifies your inner loop to make super quick testing locally and also using cloud resources. And this really changes the way you develop serverless applications in the cloud, giving you the best of both worlds, fast local development experience and using real cloud resources. It's certainly my default way to build serverless applications, and I suggest you take a look. Now, with our infrastructure as code templates, what you really want to do is make them reusable to deploy multiple copies of your app for many reasons. Giving developers their own accounts allows them to explore and allows them to build and allows them to have their own dev sandbox for building your applications. Your environments like dev, UAT, staging, and production should also all have their own accounts. And this helps isolate your workloads and give you more security from most permissive in your dev environments to least permissive in your production environments, and allows you to also control quotas and limits, and then protect production data, including PII. So templates give you more superpowers when reusing them to deploy across environments and accounts, giving you consistency across these environments. And you can effectively store config externally in something like parameter store and reference them in other templates to ensure consistency. But you also need to think bigger and manage these accounts. And so AWS organizations can help you organize your account creation. And this is something that's perfect for those platform teams to look after as part of your account vending. But sometimes you can't have multiple accounts, or you're not quite ready for that for your developers. So you can still have shared accounts and prefix resources to make them easily deployable, yet still be unique. And you can also share resources within or even across accounts. And this is great for more expensive services or ones that are hard to set up. It doesn't really have to be everything separate or everything together. You can be pragmatic in your approach. And another superpower of infrastructure as code is how it enables an automated CI/CD pipeline, allowing to use those reusable templates to deploy software automatically and repeatedly during the CI/CD process. You really want to be building as much automation into your pipeline, including integration testing and deployment monitoring. Many developers are used to pushing code into a single large service and with a huge sort of complicated delivery pipelines that has to handle all the code pushes and trying to get them into production. But if you're building smaller, discrete components and functions, particularly for serverless apps, it gives you that agility. You can then build multiple delivery pipelines. And using reusable templates allows you to release much faster because you can have a unique release pipeline for every single feature, maybe even every single commit. SAM CLI has a feature that also helps with this. SAM Pipelines allows you to securely create the resources and permissions to deploy app artifacts from your code repo into multiple accounts. And SAM Pipelines generates config files which you can use with Code Pipeline, as well as GitLab, GitHub, Actions, or Jenkins. If you're a CDK user, there many are, there's no need to feel left out. Also, CDK Pipelines is a construct library to set up CI/CD pipelines using AWS Code Pipeline. Now, I've been talking a lot about SAM, but remember, a lot of these other infrastructure as code tools from third parties also do a lot of these things as well. So if you are using them, they're still going to give you a great serverless experience. So once you're pushing things merrily into production, and here are some cool ideas to think about. Embracing ideas like testing in production and observability-driven development. So once code has passed its basic unit test validation, what you want to do is deploy to a subset of traffic and see how it compares to the previous version. And this allows you to experiment really safely, but in production. And as the super wise observability sage Charity Majors says, not testing in production is like not practicing with a full orchestra because your solo sounds fine at home. So where test-driven development is about checking your code, observability-driven development is all about the full life cycle of your code. Bringing business usability into to include it as part of observability within your software delivery lifecycle to answer questions about how your services are going to run and the business impact of every change. And good observability is super important, especially for serverless and event-driven applications. So one way to approach testing in production is using feature flags or toggles. So instead of maintaining multiple feature branches in source code, you can use a condition within your code to enable or disable a feature on demand during the runtime. And this means you can turn functionality on and off for a subset of users until you're happy to make it the default. And it makes releases and ops much simpler using canary rollout and A/B testing. And especially with testing in production and feature flags, canary testing is a great way to use guardrails for better observability. And really, you probably should be doing this more than you likely are. And we use canaries a lot internally at AWS. Cloud with Synthetics is a tool that can help, and there are certainly others. You create canaries to run tests for things as availability or latency or even dead links. And it can let you know when it finds a problem, even when you don't have any customer traffic on your application. And this allows you to discover issues when trying features before your customers do. Another good observability tip is using the CloudWatch embedded metrics format, which is a powerful capability to make your logs even more useful by automatically creating metrics from the log entries. It's an async process, so it's faster and cheaper and easy to use with Lambda. So on the left-hand side, we've got an event payload. We have a bunch of information which you want to log and create metrics from, and the right shows the log entry that has been created. It's a JSON embedded metric format, which includes information about the function invokes, and the log entry queue includes some metrics, and these are then automatically exported to CloudWatch, so you don't have to build a whole process to parse the logs and extract the metrics yourself. And there are open source client libraries available for Node, Python, Java, and C#, so it's worth taking a look and using the power of structured logging. So once you've got your structured logs created, there's even more than you can do. Log Insights is an interactive query capability for CloudWatch logs. You can run queries to visualize data. And this simple example shows all errors, but you can certainly dive deep into your logs and pull loads of information out. The link to Serverless LAN snippets collection has got some handy Lambda-specific log Insights example queries, such as finding your most expensive invokes and tracking cold starts. Another super useful set of tools that I love for removing the heavy lifting with observability and other features is the open source Lambda Power Tools, which AWS and the community has created. And this allows you to more easily add logging, tracing, and metrics to your Lambda functions with some helpful utilities added too. You can just import the libraries as part of your code or just add a Lambda layer to add it. And this really adds superpowers to your coding. And this is currently available for Python, Java, TypeScript, and under preview for .NET. So really do take a look and also consider contributing as it's open source to extend the use cases. There's plenty more serverless observability information. I did an 8-part learning path video series, Mastering Serverless Application Observability, so another thing I encourage you to take a look at. And also there's the new One Observability workshop, which is hands-on and takes you through a whole bunch of observability topics, not just necessarily related to serverless. So when taking your app from prototype to production, power your inner loop by avoiding complex emulation. Try SAM Accelerate to develop and test quickly locally with the power of the cloud too. Use infrastructure as code to your advantage with reusable templates, isolated stacks, and nimble CI/CD pipelines. Structured logging, it's a powerful 2-for-1. Get metrics straight from your logs. And also don't forget to configure your log retention. Actually, good tip I didn't mention. Best configured in those templates to not store logs you don't need and save yourself some money. And certainly look at Lambda Power Tools. There's so much functionality to make your development easier. So I started helping to frame serverless as a mindset with an operational construct, enabling you to do more. How to use the power of events to maintain state, using service integrations and the power of Lambda with all it can do. Winning with infrastructure as code with all it brings, and turbocharging your software development lifecycle from prototype into production with better cloud testing and observability. So in the time today, I said I would cover a lot. I hope is everybody still okay? You're not just too bamboozled? I hope so. But even then, with what I've said today, I couldn't possibly give you all the best practices and optimizations possible. So the linked resources page includes all the links in this presentation and many more, so you can find out all you need to do about building the best serverless applications. And I'm actually going to be adding some more links onto this over time, so it'll be an updating resource. Then to continue your AWS serverless learning, use the QR code to find more information to learn at your own pace, and this allows you to increase your knowledge and even earn a serverless badge. And for plenty more general serverless information, head over to the great serverlessland.com. It's got lots of resources. It's really everything about serverless on AWS. So thank you. I really do appreciate you taking the time to watch today, and I hope I was able to help you learn some useful best practices that the experts can do, as the experts use, so you can do even more with serverless. And lastly, if you do like deep, technical, 400-level content like this, bit of bribery, but a 5-star rating in the session survey does let us know we're on the right track. Thank you, and enjoy the rest of your reInvent.